Hi, I am Shivji, and I'll be talking about open source database architectures. The idea is that if you look at the different kinds of databases and even streaming systems, there are certain Lego blocks that are quite similar and rearranged in slightly different ways. You get a different flavor of the database. I am, like I said, I am Shivji Jha, and I am a regular software developer. I love open source and distributed systems. Been working on databases and streaming for over a decade. I head the CPaaS data platform team at Nutanix. And in my previous jobs, I have worked as a developer in MySQL replication, worked on some backend services, and then a data platform in my previous job at Swiggy and at Nutanix as well. I've contributed to MySQL and Pulsar code bases, among others. And I am a regular speaker at different open source conferences. This happens to be my third talk at the Open Source India conference. I also organize some meetups in Bangalore, and till date, I have organized meetups for Apache Pulsar and Apache Druid, so 3 of them in total. And then the idea is to go on. So we'll start with a basic typical database management system architecture. You first have a transport system that allows your database server to talk to the client. Then you also have a module that allows you to talk between different nodes in the cluster, if it's a clustered database. Next, you have a query processor. Once the query is transported from the client application to the database server, the parser will try to parse the query. Once the query is parsed, that output flows into query optimizer, where the optimizer will try to generate the best plan. We next will look at execution engine. Execution could happen either locally or remotely. It could either be scatter gather, so you ask multiple different nodes for the data they have relating to that query, or you only ask some specific ones, or alternatively, you could just execute it locally and return back, typically in a single node database server. Finally, you have the storage engine, which has multiple components: transaction manager, if it is a transactional database, log manager to manage concurrent access by different clients in the same database. Then typically, some databases also have an interface called access methods. In Postgres, it is called table API. In MySQL, it is called handler interface. Beyond which, you have your different kinds of storage engines that you can plug in. Within the storage engine, you would typically have a buffer manager, which takes care of caching data that is being written to the disk in the database for persistence. And you have a recovery manager. In case there is a node failure, then how does the database recover from it? That, of course, comes from the disk in some form. Otherwise, you will end up losing some data. So in this talk, we will first go through the transport, then execution engine, then storage engine, and towards the end, having talked about these different Lego blocks across these 3 pieces of transport, execution engine, and storage engine, we will try to see how these concepts work in some real-world database scenarios. So first off, query language. If 2 people are going to talk, there has to be an established language so both of them can understand. So that's what we do here. We have a transport protocol and we have a query language, which is a DSL, which the database server understands and provides a client library so that your client application writing in different languages can pick up the suitable library and start talking to the database. SQL first up. And I think most of the people would know SQL, most adopted query language, in my opinion. And this is a very famous quote that I found somewhere. I don't know who sort of first came up with it. So, but other than I don't claim credit for it. It says SQL behaves somewhat like a virus, your new database system will end up catching it. Kind of funny, but if you look at some of the databases that have taken a stand on the NoSQL side, a lot of them are coming up with their own SQL dialects. Of course, these are different from the ANSI SQL standards, but there are still SQL with small modifications. You can move from one database to another with some certain changes in your application that is calling the database. If you typically look at SQL from the conventional point of view, its connotation is related to relational database models, where data is organized into different tables. You also call them relations, and each piece of data is a row in the database. Example being MySQL Server, Postgres, Oracle, or SQLite is an embedded one, still SQL database, and probably one of the most used, given all the smaller tools, IoTs, your phones and stuff use SQLite. But then SQL, like I said, has found usage beyond the relational databases, which means Clickhouse and Druid are not SQL databases in the conventional sense, although these also speak SQL these days. In fact, Clickhouse only supports SQL. Druid has SQL as well as another native language. And then SQL is now actually supported across streaming systems as well. So if you look at Kafka's KSQL DB or Apache Flink or some of the older ones, so some of the newer ones in the streaming system, they all support SQL in some form, or they plan to support. NoSQL as the next query language. There were several driving forces behind the NoSQL movement, if I may say so. First being need for greater scalability than the relational databases can easily achieve. There are ways to make relational databases work on scale, but they are very easy to achieve. Secondly, if you have a very large data set, or you want to have a very high write throughput, then you typically have all these databases which classify under NoSQL databases. If you have specialized query operations, for instance, MongoDB is something that popularized document databases, Redis and DynamoDB for NoSQL databases, which are on key value, Neo4j for graph database. Additionally, if you have requirements for more dynamic and expressive data models, so you don't want to be limited by the tables and columns. For instance, MongoDB allows you to write documents which are way more flexible, and you don't really have to struggle with data migrations, kind of the most dreaded thing in the backend development world. And then there are some strict schema-related things that are forced on you when you use your relational databases. There are some good parts to it, and then there are some bad. So if you have those cases where you don't need this, then you could use a NoSQL DB. The name NoSQL is something, in my own opinion, I think it's a very unfortunate name. I mean, I am called Shivji, so you can't call the next gentleman not Shivji. It is quite weird, right? It was first used, the legend has it that it was first used as a hashtag before a meetup on non-relational databases in 2009, and then it caught up, it got popular, and people started using it. But NoSQL, I think, comes in a lot of different varieties. Over the last decade or so, there's been a lot of research and development in this space. So you have document databases, MongoDB being the most popular one, in my opinion, key value databases in Redis for caching in memory. It also has some sort of persistence, but DynamoDB, if you want persistent key value stores, is something that stands out. For graph databases, Neo4j, ArongoDB, OngDB, Amazon's Neptune, And on the column-oriented databases, you have Google's Bigtable. On the open source side, you have Clickhouse and Druid. If you are looking for database as a service, you also have Snowflake. All of these are column-oriented databases. And I'll going further explain what each of these databases are well suited to. Next up, apart from query language, we will start looking at the data model and query patterns. So first on data models, we will look at the transactional databases called OLTP here, and analytics databases. If you have to choose between which is your kind of database for the use cases you have in mind, this is slightly direct. This is table that you can probably use to decide that. If your use case mainly has read patterns, then you probably for smaller number of records per query fetched by your primary key or other key that is indexed, you could use a transactional database like a MySQL or a Postgres or an Oracle. If you are looking for aggregate over large number of records, if you're trying to maybe, let's say, set up a visualization where you sort of show a graph of an aggregate over a column, then you probably need an analytics database and OLAP system. If your main write pattern is random access, low latency writes from user input, then you are looking to get through an index like a B tree or something and get to the exact record and get that out. So that transactional systems are really good, the relational databases. If you, by nature, your writes are bulk import or event streams, then you're looking for OLAP databases. Transactional databases are typically used by end user or a customer via a web application. Analytics databases are typically used by internal analysts for their decision making. In your transactional database, you're looking for a state of data at this instant of time, while in analytics databases, you have historical data with some of the latest real-time data. Well, not real-time, maybe near real-time. Also, on the data size, if you have gigabytes to terabytes of data, maybe transactional systems, conventional relational databases will do well. But if you have terabytes to petabytes scale of data, then running analytics systems would probably benefit from the sort of modern architectures on distributed systems developed over the last decade or so. There are ways again to do it in relational database, transactional database, but your use case might be suited to that. If you have requirements that match analytics, the third column here more. Great. So we are done with the transport systems. That lays a good ground for the next topic, where we will talk about execution engine, and we will take remote execution. I think local execution is probably not that interesting. So in the interest of time, we will only talk about remote execution. And what better place to start other than CAP theorem? In my own opinion, I think CAP theorem is a wonderful place to start a conversation around your choice of databases given your requirement, but it will not take you to the ultimate decision. For that, you will need to look at more things. For the practical systems, CAP theorem I think is not enough. Having said that, Eric Brewer proposed this theorem in 2000. It says that a shared data system can have only two of the three properties among consistency, availability, and partition tolerance. When we say consistency in CAP, what we really mean is linearizability consistency, which means if you have multiple servers, in an ideal sense, when you write a data, it should be written to all the server at the same time. Well, the laws of physics wouldn't allow you that. You write on one server and you still have to transport these database changes to the other servers. So you can say that, for your users, they don't feel these differences. It has to be orchestrated in such a way. We will take a diagram to explain this further. So we have this diagram where we are talking about the football match, the final between Germany and Argentina. Let's say Alice and Bob are watching this match, and then we have a referee who declares a goal. This information gets to the leader server. The leader server prepares the transactions and thinks that it can go ahead. It sends the transaction to follower 1 and follower 2. Elias, when he checks the score, he sees that Germany has won. So the insert with Germany's score as 1 and Argentina's score as 0 has reached follower 1 before Elias makes a query from the final scores table, and he shouts saying, Germany won. When Bob, sitting with him in the same room, refreshes his app, he sees the score as 0-0 still. So he's like, what are you talking? The trouble is that insert has not yet reached follower 2 for some reason. Maybe the network is slow, or the database server on follower 2 itself is slow. But this is a case which can happen in MySQL or Postgres default replication configurations. And then this is very normal in asynchronous replications. This is fine in a practical scenario, in a lot of practical scenarios, actually, not all. So your databases, relational databases, which are famous for providing you a good amount of consistency, like your C in ACID, but they are not. So this situation is not consistent according to CAP. So this is not linearizable consistent. Linearizable consistency is actually a far more strict level of consistency. Supporting that in your regular transactional databases would make them sort of less performant. Throughput would be less. So that is why they opt for a default where they use serializable consistency and not linearizable. In the default way, you can change configurations and then try to get there. Availability in CAP means that every request received by a non-failing database server in the system must result in a non-error response. Note that it is not sufficient that some of these or one of these or everyone else but one of these return a non-error response. And then we have partition tolerance. So given the distributed nature of databases that we are talking about today, we don't really have a choice in this matter because the network lines will be cut. That's not in our control. Given the sort of cloud operating model, it's actually not even sort of in our control in any way. We can't see it, we can't touch it. So partition tolerance will always be there. So you actually have only two choices. Either you go for consistency or availability as per CAP. So this is the diagram that depicts the CAP system scenario. You have data center 1, data center 2, and then there is a network interruption between the database servers in both the data centers. So while the network is down, that's when you think of the CAP theorem. You have two choices. You either allow your users to connect to data center 1. So in our example, Alice might be connected to data center 1. And when Alice connects, knowing that data center 1 cannot talk to data center 2, you can either return the result, in which case consistency is violated, because if Bob is connected to data center 2, Bob gets a different output and Alice gets a different output. And if you sort of say that, if my data center 2 is probably not reachable, so I'll shut it down, I'll make all my users move to data center 1, in that case, you still have data center 2, which is available, but it's shut down, so it's not returning responses right now, although it was not failing. So you compromised on availability because it's still up and it doesn't return a response. Cap theorem, like I said, is limiting. It will not take you to the decision. The other aspect that you can think is this other corollary that Professor Daniel Abadi came up with. It says that if you have a partition, then you choose between availability and consistency. If you don't have a partition, at that time also, you actually have to make a trade-off between latency and consistency. If you're looking for stronger levels of consistency, then your latency will be high. Like, it's easy to visualize. Imagine I am writing to a database and it has to write to two other servers in a synchronous fashion. Then, of course, my latency will be more. While in an asynchronous replication, you just sort of prepare, send it to the followers, and then you commit, so you're faster. Moving on to replication. Why do you need replication? Because you want to keep a copy of the data close to the user. So low latency, multiple servers, some of them can fail, still the other ones are available. So increased availability, and you can spread across your queries across these database servers, so more throughput. Replication can either be single leader, multi-leader, or leaderless. In a simple leader-based replication, or master-slave as it is called in MySQL, you have Elias who updates his profile picture. The read-write queries both can go to the leader. Bob is sending a read query, so it can go to one of the followers or the leader, but the writes won't go to the follower and follower 2. If there is a write on the leader, you actually send the change log event describing the change to the followers. And again, these log of changes that you send to the follower servers could either be done asynchronously, synchronously, and semi-synchronously. These are choices that your databases will offer you. In your conventional relational databases in open source like MySQL or Postgres, again, these are asynchronous. In different setting, MySQL also offers you synchronous mode. Of course, the latency will be a little bit higher. If you're fully synchronous and your network is fragile, then it could be actually very terrible. Semi-synchronous is a way to get around that. So if you have like 5 followers, you can say that I will be fine if I get X from only 2 of them. So in this picture, we see that Elias writes, changes profile picture. This event goes to the leader. Leader is actually waiting for one of the followers' responses, which is follower 1. Follower 2's response comes later, but that's okay because the leader received one of the acts. So it's okay. You have a database in follower 1. If leader goes away, you can use follower 1. So there are different ways in which replication happens. It could be statement-based logging of the transaction in the master database. It could either be logical or your diff that happens because of the transaction on the database. That diff is stored, which is logical replication or row-based replication. Then there is wall shipping, physical replication in Postgres. Rakel also uses this. And then you have trigger-based replication. When you write to a database, you can either use triggers or stored procedures, which will give you some flexibility to write your custom code, but these are a little bit fragile. DBSM actually does a good job of fetching replication logs from MySQL, Postgres, MongoDB, at least, and then you can integrate DBSM with Kafka, Pulsar, or some messaging queue, where DBSM will pull out change logs from the database and offer to you. as messages in the PubSub world. Oracle's Golden Gate is a similar example. So what happens if your node fails in a leader-based replication, right? If you have a node that fails and needs to come up, then on recovery, what you do is, remember, when you write, when you update a row in a relational database, these changes are typically stored in the page cache of the operating system. That's what you call buffer pool as well. But these transactions are actually written to disk via the write-ahead log in Postgres or binary log in MySQL. So once you fail a node, to recover it, the database server will actually go look at write-ahead log and try to see if all those transactions, the changes those that were made as a result of those are reflected in the database state. If not, these will be first executed. The database will make changes as per these logs in the write-ahead log. After that, the database will be declared live and ready for taking queries. If you want to add a replica, it will actually get stressed trying to get every change event since the beginning of time from the master. So what you typically do is you take a backup, a consistent backup of the leader server, you restore it on the replica server, and then you attach it to the leader server. Leader server as a donor will give it the next set of transactions that came up while the restore was happening. And then only this sort of small amount of data will be sent across to the replica database, after which it can be live. For a failover scenario, it depends on whether you're doing synchronous replication, asynchronous replication, or semi-synchronous replication. So you have your set of database servers which you want to promote. Maybe it has better hardware, some other configurations which are more suited to become the leader. If you have an asynchronous application, you could lose some data. Synchronous, like I said, you probably don't have issues with failover, but then throughput is affected. A good compromise, generally, in my opinion, is semi-sync. So based on the knowledge from my spending 3 years of development work at MySQL application, what we used to advise a lot of customers at that time is that, use semi-synchronous application and use it in a way where you say, if I have 5 slaves, 2 of them reading it and sending commit is and saying, yeah, I am fine to commit it is okay. And then there are more optimizations there. We can talk later if there are if there is more time at the end. But you basically and the failover go collecting events from these and then put it in a candidate master server. And after collecting all of those and completing failover, you promote this to become the master. Multi-leader replication typically happens via quorums. DynamoDB by Amazon is something that popularized it. I would really recommend that you go through the Amazon's DynamoDB white paper. That's where these systems were thought of as practical and implemented quite successfully. Going ahead, other databases like Cassandra, React, Voldemort, those databases also use similar scenarios. So you basically say that, if I have, again, 5 replicas, well, not replicas, let's say you have 5 peers, and then you make a write. If this write is acknowledged by at least 3 of them, which is the majority, then you say, okay. When you do a read, you again say that let's say, if you really want consistency, you don't want stale data at all, you could say that my read also needs 3 acts. So even if you end up selecting 2 servers that did not acknowledge that write, you will, in the 3 servers that acknowledged your read, have at least one of the servers that got the latest write and acknowledged it. So you have the latest version of data. Every row updates and stuff are versioned. So out of the 3 read responses that you got, you look at the sort of highest version number and you use that one. At the same time, you could update the other ones which have the old data, and then you respond back to the client. We'll move to the storage engine. How do you store data in a way that your queries respond in the way you want? So if you want to make your writes fast, or you want to make your reads fast, are you going to write in batch or single events, fetch as an aggregate? According to that, data structures could be different. Your conventional relational databases typically, as a data structure, uses B trees. So all of MySQL, Postgres, Oracle, these use different variations of B tree implementations. B trees guide them to reach specific nodes. If in the random access method, it's more useful in the SDD world. So you get to the exact node and you update it there. And then for indexing, this is the default database. This could actually point to buffer pool, or if it has been evicted from buffer pool, gone to disk, it would point to the disk as well. The other kind of data structure is LSM tree, which is more optimized for writes as against B trees, which are more optimized for reads. Reads could be a little bit slower. We will see why in the pictures that will follow. LSM trees can have better compression, so less disk requirement. One of the downsides is that the compaction process that happens in the background could interfere with the writes coming from your client. It is typically used in your streaming technologies like Kafka, Pulsar, Flink, or NoSQL databases like Influx uses a variation of LSM tree implementation. Rockset uses the same as well. RockDB is a very famous implementation, which is available as an embeddable library, and it is found very wide adoption. Some systems have gone ahead for RocksDB and make something custom, but most of the systems start with RocksDB these days. So LSM trees, we talked about compaction that is good and offers you better disk utilization. Here is an example inspired by the book by Martin Kleppmann. So somebody who is probably very fond of cats. You have a data file segment 1 and 2, and we are compacting them and merging them together in the merge segment at the bottom. So you basically look at per 211, the gray boxes in file segment 1 and 2, and you pick up the last one, which is 2114 in the second row in the segment 2. So you pick up that and write per in your merge. You look at sleep, and then you take the last version among all the orange boxes in segment 1 and 2, and then you write it in the merge, and in that way you proceed to do compaction. So at any point of time, there will be a part of your data which will be compacted and a small part of your data which is yet to be compacted. When you are reading, you have to make sure that you compacted, indexed ones, you will look at them, and even the not compacted ones, that area. Typically in LSM tree implementations, you will see that you have an index in the RAM. You see the yellow part, and then you have disk side of it. The SS tables, as they are called, on the disk, they are sorted string tables. So your data is actually sorted on the disk, and additionally there is also index to different points of data. Obviously, you don't want to put every single word from your SS table into index, otherwise your index will be quite big. And there are some configurations to manage how much, depending on how much RAM you are willing to throw. So in this example, we are looking for something like handiwork. Handiwork is actually not part of our index. So we look for let's say we do a binary search in the index, in the keys in the index, and see that handiwork lies between handbag and handsome. That the second and third, the offsets for them are 102134 and 104667. So between these and the yet to be merged, somewhere there we will be looking for all the instances of handiwork and their values, and the latest out of the merged segments or the unmerged segment, that will be the value that you return. So you see that on the read, you're actually going through sorted part and unsorted part and looking at the latest data. Coming to sort of the boxes that we saw in the storage engine, a transaction manager actually schedules, coordinates, and tracks transactions and their individual steps. Log manager provides you a surety that your current access will not end up corrupting your database. Like I said earlier, your database writes in relational databases are written to memory, but the transaction logs are actually persisted to disk with every transaction. Actually, those are also, batched to a certain extent. Maybe let's say if there are multiple concurrent actions happening, and they could be sort of batched together to write a head log as well. You are basically, what you're trying to do is trying to make some sort of compromise between durability and throughput, but you have to make sure that every transaction that is committed has to be there in your write-ahead log. And then, this is called checkpointing in Postgres if you want to read further. Concurrency control, there are different ways to do it. Optimistic concurrency control, pessimistic concurrency control, and then multi-version concurrency control. MVC databases, for example, MySQL and Postgres, guarantee a consistent view of DB at some point in the past. Basically, in Postgres, if you look at it, what it does is, if you update a row, the row is actually not seen. You don't go to that memory location or disk location and change the exact value. You write this row value at the end. Maybe your B tree will be repointed to it once you are committing. The transactions that were already happening, let's say our new version of the row is given an XID called, let's say, X. The previous one, let's say, was X minus 1. So the transactions that are executing right now, they have picked up the X minus 1 version of this row, while X is still being written at the end appended. And once all these old transactions are committed and the current one modifying this row is committed, then we mark the X minus 1 version of the row as ready for cleaning up, which is called vacuum in Postgres. Auto vacuum exactly is quite famous or infamous, if I may say that. Your transaction manager, if you have a distributed database where you are allowing writes to multiple databases, then multiple database servers, then you typically use two-phase commit. So you basically, on the master database, when you get a write request, you prepare the transaction and you send it to the followers to also prepare the transactions. Once these people have prepared and they see that, we can commit this transaction, then there is a commit phase and everyone just goes and commits that. This gives us the assurity that, these databases can commit this transaction. So you just go and commit it quickly. We talked of OLTP, OLAP. In the OLAP analytics space, the data is typically stored in column-wise fashion. In this example, you see that there is some products, and across countries, what are the sales. In the row store, in the picture on the bottom left, you see that India, so in the row 1, India chocolate and 1,000 sales, you have India chocolate and 1,000 sales written in contiguous location on disk. Typically in disk, the smallest unit of access is a block. So if you are picking up one block, you get the whole row. So for your that kind of queries where you are looking for one complete row stores like MySQL and Postgres are good. If you are looking for aggregates for generally, for instance, you're looking for all the sales across countries, then the total sales number or an average of sales number across countries, for that your column storage is better, because if you want to look at all the sales numbers and then add them up in your application, then you can fetch all the sales number like you see in column store, bottom right, 1000, 2000, 4000, 5000, all those values are together. Just pick the minimum number of disk blocks in this way and get them and aggregate the data. And sometimes you also make some prepared views, like in Clickhouse you would have something called materialized views, where you actually say that, I'll pre-compute sums and keep given some grouping conditions and stuff like that. So you can serve the aggregates even faster. And then you are trading off extra disk where you are pre-computing all those results and keeping, because such queries will be there. This is a pub/sub system, a stream processing system. You typically write messages as one publisher, multiple publisher on a topic, and everyone who is subscribed to this topic will go get those messages. Typically, in this kind of system, you are looking for some of the latest messages. So those will be cached on the broker where the topic is hosted. It's costly to retrieve old data because it's not cached. You are sort of throwing away, let's think of LRU cache. You are throwing away all the latest data to get the older data in the RAM. And then it's costly for all the subscribers. Or if it is designed well, then maybe only for some of the subscribers on specific topics. Like I promised, a quick look at some of the real world databases. In MySQL, what you do is you have multiple clients. The first client comes and creates a table. The second and third clients come and insert some data. You write all of that to binary log. Then you dump it using the dump thread in the network, where IO thread picks it up and writes it into something called relay log. On the relay log, a coordinator thread sequentially goes picking up every transaction. Every worker has a queue. It will queue those transactions in the queues of the workers, and these workers will actually go ahead and execute these transactions. For parallelism, you see the binary log, the bunch of transactions that were concurrently happening on the master. You can put a group commit number to that. Transactions with the same group commit number in the relay log will be executed parallelly. Or you can say that, I want to use sort of a parallelism where transactions in one database have to be serialized, but in multiple databases can be parallelized. This is Apache Druid architecture and analytics or OLAP database. Here, what you do is when you're writing, you go through the router, then you have an overload, which is basically active passive leader based master slave or something. It writes to a host of middle manager. Every middle manager spawns up a small tiny process, or in the latest versions they have something called indexer, which is multi-threaded. This is actually a trade-off where they have gone the MySQL kind of route. MySQL is multi-threaded, whereas Postgres is multi-process. So middle manager takes all the ingestion data and puts it, indexes and puts it on your deep storage, which could be S3, SDFS, or any object store. And your historicals are horizontally scalable. These historical nodes will download something called segments, which are immutable from S3. You can't go and change the data inside the segments. If you change, let's say my segment has 1 million rows. If you want to change any one of them, then the whole segment has to be rewritten by the middle managers and go to S3 and deep storage and come back through historicals. Coordinator is the one that is again sort of active passive model, and coordinator actually helps you pull in data from one of the historicals. Like I said earlier, a lot of your prepared, ready to serve data is a historical. Some of the latest has not reached historical. Those are in middle managers. So when you read a query, you see the red arrows coming from clients. It gets through router to the broker. Broker actually combines results from historical and middle managers for the historical data and the real-time data, and serves the result to the router, which serves it to the client. Then you have multi-leader databases. It could be in a way where you are not sharding, so every server has all the data. But if you want to scale beyond a limit, which is typical of analytics databases, where you're throwing terabytes to petabytes of data, then you shard. What that means, if you have 1,000 rows, then you say that, loosely, my 500 rows will go on server 1 and its replicas, and the other 500 will go to server 2 and its replicas. And for all this coordination, you could use something like a zookeeper. Clickhouse people went ahead and forked zookeeper to write something called Clickhouse Keeper, which supports the zookeeper protocol as well. Apache Pulsar is a streaming system where your apps will publish and consume from the broker, which also has the topic cache containing the latest data. So your latest data, when you come asking for it as a consumer, it's served ready-made from the cache itself. Behind the scenes, there is bookkeeper for storing data and zookeeper for coordinating between broker nodes as well as bookkeeper nodes. So this is again a Dynamo kind of thing where you have 5 bookkeeper nodes. These are the nodes, the orange ones that store data, and you are waiting for 3 acts. So you select 3 servers which you will write, which is an ensemble in their language, and out of these 3, either you wait for all 3 responses or 2 responses if you care more about latency and less about consistency. Your act quorum is again something that you can configure, and then this way you can either try to be very consistent, where you say in this scenario, in this picture, write quorum S3 and read quorum S3, and you get absolutely consistent, or you say my write and read quorum could be both 2, and then you take some sort of risk. Like we talked in Druid, streaming databases, again, you look at streaming ingestion into Pulsar, it writes the latest stuff into journal. A background process actually goes ahead and dumps all of that indexed properly in the ledgers. So when you are consuming messages, your messages could either be in ledger, which is like your historicals in Druid, or it could be like your middle managers in Druid, which is journal here. So latest data is in journal. Journals are very small and they have their own cache and write cache. Ledgers have read cache. All of that data combined, you will get the message. And then here are the references. A couple of books that I absolutely love and are my inspiration for learning this kind of content. So that's a picture straight from my drawer, some blogs, and then some video recordings. If you have any questions, you can ask me now, or you can leave me a message on LinkedIn. And if you are interested in this kind of content, you could join a Telegram group where I share all the curated list of content that I read on internet.